Good afternoon, everyone, and thanks for tuning in. This talk is going to discuss how we're using recently developed high-resolution terrain models to improve our mapping of glacial landforms and integrate with our 3D sediment mapping initiatives at the Ontario Geological Survey. We will briefly outline the nature and coverage of the recently released LiDAR data that's changing what and how we can map as far as glacial landforms go, and provide some examples, and then outline some of the challenges we experience in linking them to our subsurface modeling efforts. Before I start, I do want to take a second and recognize the outstanding work that the Ministry of Natural Resources and Forestry Elevation Group, along with OMAFRA, has done in providing these data sets. And a huge thank you to Key Young for getting it all together and basically delivering it to my lap so I get to have all the fun and work with it. So this map shows Southern Ontario and shows the distribution of most of the new terrain data. And as you can see, we've basically completely covered Southern Ontario with new data sets. If we zoom in, we can take a look in this area, and this is what things looked like prior to 2013. The landscape looked pretty nondescript in a 30-meter cell size. But now with the new LiDAR and other topographic data we have, this is the kind of information we're getting. And obviously, if your job is to map landforms and try to understand past processes, life's a whole lot easier with this new stuff. So LiDAR allows us to map landforms like never before. This updated inventory greatly improves our understanding of ice dynamics during deglaciation, and an improved picture of what ice was doing gives us modelers a much better framework for understanding the sedimentological changes and links between stratigraphic units comprising landforms and connections with regional buried sediment units. So taking a look at the difference as far as what we see from 30-meter to half-meter grid cell size elevation models, here's an example of the complex ice dynamic changes we can see in southwestern Ontario. This is kind of near Listowel. So what we can see here is we've got a buried esker that was deposited first. This was overridden by ice flowing towards the southeast, creating this beautiful streamlining we see on the landscape through most of the frame. Following that, we had two very small, younger eskers deposited on top of the till during the end of that phase of ice flow. And after that ended, we have a younger advance coming out of ice coming out of the Lake Huron Basin that overrode that portion of the till plain to a limit at the Mitchell Moraine in this area. And then another series of eskers were deposited on top of that younger till sheet. So we get, just from the data itself, a very good understanding of the different phases of ice and the different landforms that were created at different times in a given area. If we move just a little bit further southwest, we can see a nice series of moraine ridges overlie a streamlined till plain, and in this area they're heavily dissected by glacial fluvial channels. Here we also see close relationships between moraine ridges and eskers, but several groups of closed depressions are observed beyond the outlines of the moraine footprints. And in this area, there are actually clusters of sinkholes, which have been reasonably well studied. There's also a single isolated sinkhole in the north, which is the famous or infamous Tucker-Smith sinkhole, depending on how much work you've done on it. And obviously, being able to denote individual and clusters of sinkholes is incredibly useful practice when we're dealing with, looking at features that are relevant to groundwater investigations. And here's a great display of the complexity we can now see within moraine systems. We no longer have to treat them as these big regional scale features. We can zoom in and see all the different components. So this is the Paris Galt moraine along the southeast corner of Guelph. And it was historically viewed as two ridges, one sort of in the west and one in the east. But a better picture is now emerging thanks to the LiDAR data sets in this area. So now we can see up to 5 potential individual ridges that make up this part of the moraine system. Those are outlined in the dashed lines. We see numerous closed depressions, which are shown in the X areas here. There are many, many more in this frame. But then there's also a different kind of closed depressions. These are larger features, and these actually look like ice-walled lakes, which are formed in a much different manner than the normal kettle holes that we're typically used to seeing. And they have a very different infill, which gives them a very different sort of function as far as their recharge potential goes. Numerous meltwater systems are observable both at surface and inferable in the subsurface in this part of the moraine systems. These are, channels that truncate the moraine ridges, or areas where we can see deposition of outwash fans along the flanks of those moraine ridges. And for those curious, there's a great paper by Emmanuel et al. Who discussed some of the stratigraphic and morphological complexity in this area of the Paris Galt moraine. So obviously at the OGS, we're not solely in the business of doodling on LiDAR data sets. The bread and butter of what we do is our three-dimensional sediment mapping program, which relies very heavily on the drilling of continuously cored boreholes, which we get beautiful preservation of all the sedimentary structures from surface all the way down to bedrock, so we can characterize the full stratigraphic succession in different areas. These boreholes provide the critical insights into the local characteristics of glacial landforms and sediment units. And while the surface sediments are important and they allow us to delineate the features, it's the bulk composition of these landforms that really is what we're more interested in. So this is an example of a project that's been kind of underway but on the back burner for a while, and it's the development of a moraine map for southern Ontario that is classified based on their composition. So sand and gravel chord features versus till chord features. And the next part of this talk here is going to outline how the two data sets, the LiDAR and our chord boreholes, work together to allow us to help build a better picture of the stratigraphy of these important landforms. So we'll take a look at a few of these highlighted in the blue lines here and just get a sense of how these two data sets sort of work together. So the first stop is the Orangeville moraine, which is a large interlobate feature shown here. And looking at the high resolution terrain data, we can outline an area that's got a very typical characteristic morphology for these interlobate features. And a borehole that was drilled right through the center of this feature shows the typical succession of sand, silt, and gravel that is characteristic of these features, stretching from surface down to a fairly significant depth. But then if we look beyond the margins of the obvious parts of the moraine to the west and east, we see that we go down through streamlined till plain in the west, and beneath that, equivalent deposits of sand, silt, and gravel are encountered on both sides. So it's the extent that we would map from LiDAR alone is much smaller than the actual buried footprint of the moraine, which has been discovered through drilling and 3D sediment mapping initiatives by Abigail in Orangeville that was published in 2016. So if we move a little bit further south, looking along the Paris Galt moraine, in the north, we see a very typical hummocky kettle topography that comprises a ridge that overlies streamlined till plain. And here, a borehole drilled through the succession reveals almost entirely sandy silt till with just a few gravelly interbeds. If you compare that to the south, looking at the LiDAR data, we see a very different type of morphology in this region, a single ridge that is kind of steep flanked and heavily dissected. And when you look at the stratigraphy uncovered in a borehole here, it's very different, almost entirely composed of stratified material. And here we've got two different potential aquifer systems, both a shallow and a deeper unit. And if we move further east to a younger moraine, southeast of Hamilton, again, we've got a very continuous morphology along this feature, and in the eastern segments, we see a very typical or expected succession of sediments of fine-grained diamictons and silt and clay deposits. But as we move further west along the feature, something of a surprise in that we had a little bit of diamicton at the very top, but then the bulk of the feature, the bulk of the ridge is actually composed of a coarsening upward succession of tens of meters of sand in this area. So another example of where the boreholes are shedding a different light than the LiDAR data alone might have inferred. So while moraines are the most dominant landforms, we've shown some examples of how the high resolution data is shaping our understanding, and individuals either confirm or reshape that picture of what's going on in those features. But ultimately our job is to build models. And obviously 4-inch diameter boreholes and half-meter grid cell LiDAR data sets don't directly translate into 3D models where our blocks are 100 by 100 meters. So despite that, these data are still a critical component of our model development as they frame kind of what's realistic to expect in the subsurface. And in addition to that resolution crunch, going from mapping to modeling faces numerous other challenges. A model by definition is going to oversimplify complexity. And any model is limited by its scale and scope. So what you get out of a site scale study won't be the same as what you can expect in a regional scale investigation, which again won't be the same as what you're going to see in a provincial scale model. And this is illustrated pretty nicely in a north to south cross section, again along the Periscalt moraine. Here we see that the sediment units that comprise the moraine are straightforward within individual model areas of the Orangeville-Fergus, Waterloo, Brantford, and Niagara region. But when you try to connect the lines in between these areas, things get a lot more complicated. The moraine building process was different along different parts of the ice margins. So trying to connect the lines between different sediment units gets pretty ugly and pretty challenging in places. Now, knowing what exists on the landscape is one thing, and it's getting easier and easier to map the landscape, but sometimes modeling is another ballgame altogether. The larger the model, the more information you're going to lose, and our model cells simply can't capture many of these small eskers, individual moraine ridges, closed depressions, all that sort of fun stuff that we like to pick out on these high-resolution data sets. But knowing where those are still helps us target individual drilling sites and constrains our model development. So even though this information is getting swallowed up by the sort of coarse resolution of our models, you can still find that data within our miscellaneous data releases, and it's explained in our groundwater resource study reports, which are sometimes the only way we can actually account for the variability within our model units. So though we are well aware of the complexity and heterogeneity of glacial sediments that creates obvious problems and issues in understanding and assigning significance to variations in our model units. At this point, based on the technology we have and the data that's available to us, this is still the only way we're able to really characterize those spatial changes. So to kind of wrap things up, this was a whirlwind tour of some fun landforms and some fun stratigraphic successions we've been uncovering over the last, getting on 2 decades. New data is always helping us to understand our geologic history and better constrain and predict sediment characteristics and trends. But not all the data and knowledge we can gather is effectively included within the models themselves. So here we're hoping to continue to build on integrating data into our modeling efforts. And again, that data might not make it into the model itself, but it's always sort of available if you know where to look. And sometimes that in itself isn't easy. So just want to reiterate that we are always available and more than happy to engage in any discussions and answer any questions you might have with some of the weird and wacky stuff that's going on in the Quaternary pile in Southern Ontario. So with that, I will wrap it up, and here's our emails, and you can absolutely feel free to get in touch with us anytime. Thanks.